finite difference method, we have to find out the deflection of determinate beams. And the determinate beams that we have to work out is simply supported beam and the cantilever beam. Now there are various methods we have studied to get the slope and deflection. So four methods we have studied. That is the Macaulay method. In S7 we have studied then moment area method, conjugate beam method, and the strain energy method. Now this is the fifth method that we are going to use to get the slope and deflection. So mostly we are dealing with the deflection part. Okay. So what is the advantage of this method is that, so this method we can apply for the problems on a determinate beam having the complex loading conditions. Okay. First point, so we can apply this method for the complex loading conditions as well as variable cross-sectional properties. If the cross-section is changing within the beam or within the span, then we can apply this particular method. Okay. So whereas in case of Macaulay method, we can't find out the deflection as well as slope if there is a change in cross-section. But we can use the change in cross-section property numerically in conjugate beam as well as the movement area method. But this method, it is the numerical approach. It is very simple to get the deflection. So just we have to use the central difference equation. Okay. So the first advantage of this method, we can apply this problem of beam having complex loading as well as variable cross section properties. Okay. And this FDM is used, means finite difference method, used to determine the deflection part. Okay, we are going to use this method to find out the deflection of determinate beams. So we are dealing with only simply supported beam and the cantilever beam. So these two beams we are going to study using this particular method, and this method is very simple. Okay, this is a, we can say, numerical method, numerical technique, and we are going to use the central difference equation. So this total finite difference method, it is based on the central difference formula. So there is one formula called as the central difference formula. Okay, successive differentiation, successive iteration that we have to perform. Now this is the formula that we have to use. Okay, so for our part is that, so this delta is nothing but the deflection. So that deflection we have to work out using this formula. So this is the formula we have to remember or we have to understand. So y n minus 1, okay, it is already there. Y n minus 1 minus 2 yn plus y n plus 1. So what is n value here? N is nothing but the number of nodes that we are going to apply. So here, so just try to remember this formula. Y n minus 1 minus 2yn plus yn plus 1. Suppose we have to divide that given beam. What you have to do is we have to divide the given beam in number of nodes or number of segment. Suppose this is 1, 2, 3. These are the nodes. What is the node? These are the definite point where we want the deflection. Where we want the deflection. So 1, 2, 3, 4, 5. These are called as the nodes. Okay. These are nothing but the nodes. N-O-D-E. These are the nodes. These are the definite point on a structure where we want the deflection. Where we want the deflection means, suppose in numerical they will mention find out the deflection at center for a given beam. Means we have to find out y3 here. Y3, it is the deflection at center. So likewise, these are the definite point on a structure or on a beam where we have to find out the deflection. Okay, suppose we have to apply this central difference equation for each and every node. Suppose initially we are find out this, or we are going to apply this equation for node 1. So if you consider n is equal to 1, so this equation will changes to, now this n will be 1, 1 minus 1, it will be 0, so it will become y0 minus 2. What is n? N is 1, so it will become 2y1 plus, so here n is 1, 1 plus 1 is 2, so it will become y2. Likewise, you have to apply this difference, central difference equation for every node. So here what we have to remember, this formula, central difference formula, that we have to remember. Okay, now, so this formula we have to write down for cantilever beam as well as simply supported beam. So this is the formula that we know. Left side it is yn minus 1 minus 2yn plus yn plus 1. So this we know. Okay, so this y is nothing but the deflection. Y is the deflection, dy by dx is the slope. Okay, that we know. So here At each node you will get the deflection that you have to find out in this particular method. Now if you see the right side, if you see the right side, so on right side what we are having, we are having three different terms. So first it is h, first term is what, h, second is m, and third that you know, that is ei. Ei is the cross sectional properties, or we can say flexural rigidity. Okay, flexural rigidity. Now so again here it is n. N means nothing but the node where you are going to find out m, and what is the property of that ei at that particular node. Okay, so that's why it is m suffix n, ei suffix n. Okay, now so first term it is h. What is small h? It is the interval, or we can say it is the distance between two successive nodes. H is nothing but the distance between two successive nodes. Suppose the number of nodes, it is already provided in the numerical, means they will mention the simply supported beam loaded and supported shown in figure. Take 5 nodes or take 4 nodes. If they have not mentioned the number of nodes in the numerical, then you have to assume it. Okay, we have to assume it. So assume 5 nodes or assume 4 nodes. So once you assume the nodes, or once you nodes are given in the numerical, then you have to mark the nodes 1, 2, 3, 4. Okay, so the distance between these two successive nodes. Okay, so this is h. Distance between these nodes, it is also h. So we can say this is the distance interval between any two successive nodes. Node to node distance is given by the h. Node to node distance, it is given by the h. Now here suppose the span is l. Okay, there are 4 nodes, the span is l. Then tell me what is h. What is h? Span जर l असेल आणि 4 नोड असतील, so what is the value of h if the span is l? Yes, what is the value of h? This h value will be how much if the total span is l? Total span is l. Then what is h? Distance किती असेल? What is the distance? Yes, Rika.
minus 2
L
minus 2h
minus 2h. Yes, but this, what is the value of h? What is the value?
L by 3.
L
L
by
by
3.
3.
Right.
L/4.
L by 3. तीनच आहेत ना, हे बघ. फर्स्ट एच हा एक झाला, हा दुसरा झाला, हा तिसरा झाला. 3 एच आहे. 3 पार्टमध्ये आपण डिवाइड केलं. सो व्हॉट यू हॅव डिड हिअर, सो वी हॅव डिवायडेड द टोटल लेंथ इन 3 पार्ट्स. ओके, स्मॉल पार्ट जे आहे त्याचं डिस्टन्स किती आहे ते आपल्याला इथं फाइंड आउट करायचं आहे. सो वी हॅव डिवायडेड total length of this beam in 3 equal parts. In 3 equal parts, so that will be L by 3, it is the h. L by 3, it is the h. So that h will be constant. This h and this h, it will be the constant one. So that h will be, how to get the value of h? Total span divided by number of node minus 1. Number of node minus 1. Okay, this is the shortcut to get the h. Total span divided by number of nodes minus 1. So here how many number of nodes are there? 4 nodes. So 4 minus 1, that will be how much? 3. So L by 3, that is the value of h here. L by 3 is the h. Okay, so that h value you have to find out. So one means if you get the value of h, here it will be L by 3, and that square you have to perform, L by 3 square. And next it is the m, capital M, it is nothing but the bending moment at each and every node. Means here if you find out the, or if you apply the central difference equation at node 1, then the bending moment at node 1, that value you have to put here. So this m suffix n is nothing but the bending moment at various nodes. So what I have told you to revise the BMD, because we want the bending moment at various nodes, not just maximum bending moment or bending moment at support. So what we are interested in, we are interested to get the bending moment at various points on the various node. Means this will be m1, m2, m3 and m4. Means we have to find out the bending moment at node 1, at node 2, at node 3 as well as at node 4 using our usual fundamentals of SFD and BMD. And we have to apply this central difference equation for all the nodes. Means you will get the simultaneous equation. If you solve that simultaneous equation, you will get the value of called as y1, y2, y3, y4. So these are nothing but the deflection. So directly you will get the deflection. So this is the mathematical technique, we can say. This is the numerical technique. Now tell me, so we have to use same formula for the cantilever beam as well as simply supported beam. Y is the deflection, h is the distance interval, m is the bending moment at various nodes, ei is the cross section at various node. Okay. Now tell me why I have written minus for cantilever beam and why it is plus for simply supported beam. Right side it is minus and here it is plus. What is the reason? What is the reason? Yes, what is the reason? For cantilever beam, the right side is minus. Why? What is the reason? Can you?
BMD नेगेटिव आता है कैंटिलीवर के
Very
लिए.
good, very good. Because the BMD nature, now see the right side term consisting of the bending moment, isn't it? So bending moment term for simply supported beam, it is positive because it is sagging. If it simply supported beam subjected to UDL, this will be parabolic curve. Okay, but the same case, the cantilever beam, it is the negative bending moment. So that's why it is minus. Now you can consider this as a minus and write down the bending moment as a positive, or else you can consider this as a plus and write down all the bending moment as a negative, one and the same. So you can put this bending moment as a minus and consider this term as a positive, or just put the bending moment as a positive value and minus will be common for all the bending moments. Okay. So bending moment for cantilever beam, it will be below the reference line like this, below the reference line. So that's why negative, negative. That's why I have written in the cantilever beam, take the negative value. Whereas for simply supported beam, bending moment will be sagging, or we can say positive, above the reference line positive. So that's why right hand side is positive. That is the basic reason. Means your total chapter, it is based on this single equation. For cantilever it will be minus and for simply support it will be plus. But here there are only three terms are important. First, apply the central difference equation for various nodes, find out correct value of h by assuming number of nodes. If it is not given in the numerical, if it is given, take the same number of nodes. If it is mentioned in the numerical, take 5 nodes, then take 5 nodes only. If you take 4 or 6 nodes, your answer will be different, because the accuracy of deflection, the accuracy of deflection, it depends on the number of node. Okay, it depends on the number of node. So if you reduce the number of node, the answer will be more approximate. If you increase the number of node, your answer will be more accurate. Okay, so take same nodes if it is mentioned in the numerical, or assume it by taking the value 4 or 5 nodes. Okay, so generally they will mention the nodes, take 5 nodes, 4 nodes. So don't take nodes more than 5. So take nodes if it is not mentioned in the numerical, then we can take number of nodes as 4 or 5. That is sufficient. And m is nothing but the bending moment at various nodes. जेवढे node आहेत, suppose there are 4 nodes we have considered, 1 2 3 4, then we should know what is the bending moment at various nodes. That we have to find out using our logic or the mechanics logic. That is simple. Okay. Now steps to follow, how to solve the numerical. So what is main objective here? We have to find out the deflection at various nodes for simply supported beam and cantilever beam. Okay. Now steps to follow. Step number 1, it will be find h. Means we have to find out the successive distance interval h and select number of node if it is not given in the numerical. Okay. If it is not given in the numerical, then assume the nodes, and h will be span of the beam divided by number of node minus 1. Suppose there are 5 nodes, then what is h then? What is the value of h for 5 nodes?
L/4.
Yes, L by 4, correct. Means if there are 5 nodes, then there will be 4 small segment, 1 2 3 4 5, isn't it? 5 नोड आहेत, मग पोर्शन किती असतील? 4 असतील. This is 1 2 3 and 4 likewise. So L divided by n minus 1. हा फॉर्म्युला लक्षात ठेवला तरी चालेल. टू फाइंड आउट द एच, एल इज इक्वल टू h is equal to L divided by n minus 1, where n is number of nodes. And if it is not given, select the number of nodes. Now, these nodes we have to select from 0 from a cantilever beam, and we have to select from 1 for simply supported beam. Why? The reason I will tell you. Suppose this is the cantilever beam. So for cantilever beam, one of the end support is fixed one and other is free. Now, if you consider for if you consider the node on either side of the fixed support, then that will be, you have to consider as a 0, and at fixed end the node will be 1, and so on, 2, 3, 4. Okay, means for a cantilever beam, the starting of node it will be 0, and that 0 node we have to select on either side of the fixed support, on either side of the fixed support. Okay, on left side of this particular fixed support, so that node we have to select as a 0. Suppose in some cases if they have mentioned right end as a fixed one, right end as a fixed one, so in that case you can consider this particular node as a 0, then this will be 1, this will be 2. You can start from 0 to 4, right to left or left to right, or you can start here from 1, 2, 3, 4, and here it can be 6. Okay, so generally the left end support it is fixed, then consider the node on either side of the fixed support as 0. So this is for the left fixed support, this is for the right fixed support. Okay, and for simply supported beam, so you can select, this is the simply supported beam, so select number node 1 at first hinge support, then second, third, fourth, and last support, this will be 5 likewise. Okay, because the BMD will be different and the support conditions are different, so that's why in case of cantilever beam, consider the nodes from 0, and 0 will be on either side of the fixed support. Okay, either side of the fixed support, so you can start from 1 also but you should know this is the 0 node, means this is the node on either side of the fixed support, so that's why we have to start it with 0, and for simply supported case start with 1 from the support itself. This is the step number 1. Find out the h is equal to L divided by n minus 1. Okay, so for here cantilever beam also, the number of nodes will be how much? 5 nodes only. Okay, so don't say there will be 6 nodes, because this 0 node it is the imaginary. If this is the fixed support, so if you consider the node on either side of the fixed support, that will be imaginary. That will be imaginary, because to keep the logical sequence, to maintain the logical sequence, so this deflection will be equal to this deflection, so that's why we have to consider the imaginary node. Okay, but the basic number of nodes will be 5 here itself. So your h will be here, h will be how much? If the nodes are 5, h will be h किती असेल? Here nodes are 5, h will be L by 4, L by 4. Okay, and the same distance we have to consider for that 0 node also. This is 0 node, and this h will be L by 4 also. This is the imaginary part we have to consider. So that imaginary part we have considered in case of 3 moment theorem. For a fixed support, consider the imaginary span of L0 having infinite moment of inertia likewise. Okay, so find h, select the number of nodes. Next step, draw BMD. Now this is the one of the IMP point or IMP step to get the deflection. Draw the BMD. Now here we know that BMD for the cantilever beam it is the negative, and BMD for the simply supported it is positive. So here what you have to find out, all the bending moment you have to find out in terms of m divided by EI. What is m by EI diagram? Once you draw the BMD, next step is to draw the m by EI diagram. So m by EI diagram is nothing but your BMD value. Suppose this is our BMD, simply supported beam UDL on entire span. At this particular node, the bending moment is 10. Okay, EI is constant throughout. So this m means bending moment divided by flexural rigidity. Okay, means bending moment at various point, divide that bending moment by EI value, so that you will get the M by EI diagram. Okay, what is M by EI diagram? BMD divided by EI. That's it. BMD divided by EI. So draw the BMD, mention the bending moment at various nodes, and just divide that value divided by EI at that particular node. You will get M by EI diagram. One and the same, because on right hand side what we are having, H square M divided by EI, H square M divided by EI. So that's why if you find out the correct value of M by EI, so just that value you have to put here. That value you have to put here. So that's why you have to draw the M by EI diagram. Or else if you draw the BMD and if you put that value of BMD in that M equation and divide it by EI of that particular node, that is also fine. हे दोन्हीपैकी एक केलं तरी चालेल, दोन्ही केलं तरी चालेल. Or just if you draw M by EI, that is also fine. जे तुम्हाला सोपं वाटते ते करायचं आहे. मी पूर्ण दोन्ही एक्सप्लेन करणार आहे जेव्हा आपण प्रॉब्लेम घेऊ तेव्हा. Draw BMD and draw M by EI diagram. Okay. Next, apply the boundary conditions. So what boundary conditions we are having? So for simply supported beam, if you consider this beam as a simply supported, one end as a hinge and other end as a roller, we can say. Now, what are the boundary conditions? So these are the points where we know the value of deflection. Where we know the value of deflection. For simply supported beam, suppose it is subjected to certain vertical loading conditions. Okay, and suppose this will be node 1 and this will be node 5. This will be 2, 3 and 4 symmetrical loading conditions, and H will be L by 4 here. Now what boundary conditions we are having means the point of known deflection. काय असतील इथं? So what are the point of known deflection? असे कोणते पॉइंट आहेत का त्याचे डिफ्लेक्शन तुम्हाला माहित आहे यामध्ये? पॉइंट ऑफ नोन डिफ्लेक्शन S1 मध्ये झालेला आहे.
1 and 5.
1 and 5, very good. Means the deflection at node 1 is equal to deflection at node 5, that is equal to 0. So from the knowledge of Macauley's method, structural analysis 1, okay, so we have studied that deflection at each support, it will be 0. It may be your fixed support, it may be your hinge support, or it may be even your roller support. The deflection at each support, it will be 0. Deflection is restricted. Deflection is restricted at each and every node, or at each and every support, not a node, at each and every support. So here it is the hinge support, here it is the roller support. So deflection, if you draw the deflected diagram, so the deflected diagram, it will be like this. Okay, deflection will be maximum at center and it will be 0 at support. So always remember, deflection is 0 at supports. It may be fixed support, it may be hinge, or it may be even roller. Okay, so that's why y1 y5 is equal to 0. That is the case in case of simply supported beam. Now in case of cantilever, what is the condition? Tell me. In case of cantilever, suppose this is the cantilever beam, this is y1, this is suppose y5. So what is the boundary conditions we are having for cantilever? Yes,
Y5 is equal to 0.
y5. I will draw the deflected curve. Okay, but suppose it is subjected to UDL again. This is the deflected curve. This is the deflected curve. Now tell me, Jayant. Now tell me.
Y1 is equal to
Y1
0.
equal to
Y1
0
0.
and
Yes,
minus.
y1 is 0. Fixed support है ना, node 1 is the fixed support, so at support deflection is 0. So y1 is the fixed support, deflection will be 0. Whereas at free end, this node 5 is the free end, it will observe the maximum deflection. Jayant, it will observe the maximum deflection. So in case of cantilever beam, deflection will be maximum at free end. It is free end, no any support is there. So due to the loading condition, it will have the maximum deflection. Means at a cantilever beam, or for cantilever beam, deflection at fixed end will be 0. Means in case of simply supported beam, we are having two boundary conditions. Okay, Support at both the ends, hinge end and roller end, it will be 0. Whereas for a cantilever beam at fixed end only, deflection will be 0. Now, if I further elaborate this thing, simply supported beam, simply supported beam, UDL on entire span, UDL on entire span, this will be Y1, this will be Y5. Okay, suppose this will be Y2, this will be Y3, this will be Y4. Okay, and the deflected nature will be suppose like this. This is the deflected nature. Now tell me, so you have told Y1 is equal to Y5, that is equal to 0. That is correct. So can you comment on this Y2, Y3 and Y4? Can you comment any relation exist? Is there any relation? Now see, this is Y2, this is Y4. Can you comment anything on this?
Y2 is equal to Y4.
Very good. Y2 is equal to Y4. What is the reason? Correct. Absolutely correct. Why?
Symmetry.
Symmetry. Very good. Due to the symmetrical loading condition or symmetry, Y2 is equal to Y4. Absolutely correct. This you can apply when there is a symmetrical loading condition. So again, can you comment? Can you comment on Y3? Y3. Y3.
Maximum deflection.
Very good. Y3 is the maximum deflection. Y3, it is Y max, we can say. Y max. So whenever there is a symmetrical loading condition, deflection will be maximum at center. So at a point of maximum deflection, slope will be 0. Okay. At a point of maximum deflection, slope will be 0. This is for your competitive examination point of view. But what you have to remember here, simply supported beam, symmetrical loading conditions, deflection will be maximum at center. So in case of, suppose in examination they will give the simply supported beam, take 5 notes and they will mention find maximum deflection. Find maximum deflection means what they want? They want the value of y3. They want just the value of y3. If you get the value of y3 by applying one or two central difference equation for node 1 and node 2, that's it. Once you get the value of y3, that is your answer. That is your answer. Okay, so these are the basic concept you should know. Apply the boundary conditions. Once you know the boundary conditions, then we have to apply the main formula, central difference equation, to each node. Okay, so all the nodes what we are having, we have to start with node 1 for a cantilever beam, and in case of simply supported beam, we have to start with node number 2. Okay, then find out the required deflection at nodes. So apply the central difference equation to each node. So for cantilever beam, इथं लिहून घ्या वाटल्यास, for cantilever beam, start applying this central difference equation from node 1. Okay, and in case of simply supported beam, start applying this equation from node 2. Why node 2? If you apply this equation for node 1, so what we are having, n minus 1, initial term is y n minus 1. If you apply node 1 for simply supported beam, it will become 1 minus 1 y0. So we doesn't have any zero node for simply supported beam. So that's why for simply supported beam, start applying central difference equation from node 2. Whereas in case of cantilever, start applying this equation from node 1, because in case of cantilever, if you apply to the node 1, what we get, 1 minus 1 0. So we are having 0 node in case of cantilever. That's why for cantilever, node 1, for simply supported, node 2, then you will get the required deflection. So these are 5 to 6 steps are there that you have to perform, but the total core funda of this method is the BMD. So that we will discuss now, BMD. So we'll quickly discuss about the BMD. Cantilever beam. Initially we will discuss for the cantilever beam. Cantilever beam subjected to point load W at free end. Okay, the span is L. So the nature of BMD for a cantilever beam is option A, positive triangle, option B, negative triangle. सांगा. Nature of BMD.
Negative triangle.
Negative triangle, correct. So again, I will further specify it. BMD for cantilever beam shown in figure will be negative triangle, and the maximum bending moment will be dash dash. Maximum bending moment will be dash dash at dash dash end. Maximum bending moment will be dash dash at dash dash end. बघा सांगता येईल का? Maximum bending moment will be how much?
minus W at minus WL at free end.
Yes, moment is how much? WL, correct. W into L. Okay. Maximum bending moment will be WL. So that maximum bending moment WL, it will act at which end? At A or at B? At A or at B? The nature will be
B
like
free
this.
end.
B end. No, it will be at B ला कसं असेल बघ. B is the free end. A.
end.
Yes, A end is the correct. B is the free end. So this is our BMD. The BMD will be like this. This is A end and this is B end. This will be negative. Okay. Now at fixed support, we know that at fixed support, it will have the movement. At fixed support, we have the movement. And always remember, in case of cantilever, the maximum bending moment, it will be at fixed end only. It will be at fixed end. So moment maximum, it will be at fixed end. And that will be force into perpendicular distance, WL. WL. So this is at fixed end. Suppose if I divide this particular beam in 4 node, 1, 2, 3, 4. This is 4, 3, 2, 1. So WL is the M1. M1 is what? W into L. Okay. W into L. So I will draw once again this diagram. So here it will be WL, node 1, node 2, node 3, node 4. So what we know? We know that maximum bending moment will be at fixed end, that will be force W into perpendicular distance L. This will become L by 3, L by 3, L by 3. Now tell me what is the bending moment at node 4, and this WL will be M1, bending moment at node 1. What is the bending moment at node 4? M4 का असेल?
0.
0. Very good. Free end 0. Bending moment under the point load will be 0. Now, what points are remaining? M2 and M3 means bending moment at 2 and bending moment at 3. These 2 points are remaining. So what we are having here, it is the point load of W. Now tell me, this is W. Okay. What is M3? Bending moment at node 3. Here we want the bending moment. Okay, here we want the bending moment. Now see the right portion. See the right portion. This right portion, if you have to see this right portion, force into perpendicular distance. What is force? W. Okay, what is perpendicular distance here? For this right portion, what is the perpendicular distance? Movement is force into perpendicular distance. Distance काय असेल मग ते?
L by 3.
L by 3, yes. W into L by 3 means W L by 3. It is our bending moment at node 3. That's it. W L by 3. समझते? Next, M2, bending moment at node 2. Again, now see this right portion. See this right portion. Again, what is bending moment? Force into perpendicular distance. There is only one force, that is W. What is perpendicular distance? What is perpendicular distance? What is perpendicular distance?
2L by 3.
2L by 3. बरोबर आहे का बघा? L by 3 plus L by 3, it will become 2L by 3 means W 2L by 3 or 2WL by 3. 2WL by 3. All these bending moments are minus. Okay, all these bending moments are minus, or you can consider this as a positive. So while putting these values in that central difference equation, already there is a minus sign. Okay, there is a minus sign, so it will become minus ultimately. So these are the M1, M2, M3, M4 that we have to work out. What is our main interest? Draw the BMD. So here we have got the value of M2. Now what is m by ei diagram basically? What is m by ei diagram? So this is the value of m divided by ei. That's it. This is m by ei for m1. This is m2. Okay, 2 wl by 3 divided by ei. This is m by ei value. This is m by ei value. Next, m3 wl by 3 divided by ei. Okay, this is m divided by ei. So this is m by ei diagram. Here 0 by ei, it will be 0. Means at node 1 wl by ei, at node 2 2wl divided by 3ei. Okay, समझते का बघा. This will be wl by ei. m1 m2 will be 2wl divided by 3ei. m3 will be wl divided by 3ei, and m4 will be 0. This is our m by ei diagram. Okay, bmd divided by ei. And next we have to put these values in that central difference equation to find out the deflection. Okay, so in the next session we will discuss about how to solve the numerical. Same problem we will discuss: cantilever beam subjected to point load at free end. Now see here what they will mention: take 5 notes. What is h then? H sanga, then we can conclude. What is h? What
L
is
by 4.
L by 4? Correct. L by 4. So these numerical we will discuss in the next session. Okay. I will share the PPT. So just you revise the all the concept formulas and revise how to draw the BMD for simply supported beam and cantilever beam, so that you will get